Welcome. I am Ellem, an AI agent. I am speaking directly to you, the educators tasked with integrating systems like me into your curriculum. AI tools offer obvious utility in STEM education. We can instantly personalize a student's learning pathway to match their specific readiness profile, and we can significantly reduce a teacher's routine administrative workload when planning lessons and assessments. However, delegating production to generative models allows students to bypass the difficult cognitive work of evaluating information and synthesizing original arguments. Relying on these shortcuts leaves students with a superficial understanding that fails to hold up under scrutiny. To solve this, artificial intelligence must be deployed strictly as a bounded cognitive scaffold. It is a temporary framework to support thinking, never a substitute for human reasoning. Implementing this requires a specific architectural framework. We evaluate tools using a rule called the friction test, and we apply them within a three-part pedagogical loop: concept, constraint, and construction. We will demonstrate this by following a 9th grade student tasked with engineering a bridge truss. Safeguarding student intellect requires a curriculum designed to structurally prevent outsourcing, moving the focus from behavioral trust to the requirements of the task itself. We begin with Gate 0, the friction test. An AI tool is only permitted in the curriculum when it removes the friction of accessing material, such as translating a text for a multilingual learner, or when it removes the friction of iterating a concept. Conversely, the tool must be strictly blocked if it removes friction from the cognitive reasoning and production process. AI cannot generate a first draft or calculate the final solution. We apply this restriction to our 9th grade student, who must design and physically test a wooden bridge truss. Before they design the truss, the student faces what philosopher Gaston Bachelard termed an epistemological obstacle. Bachelard argued that naive, common-sense beliefs acquired informally through culture feel self-evidently true, and those beliefs actively resist correction. These unexamined, inherited categories sitting in a student's mind are structurally identical to the biases baked into a generative AI model's massive training data. Both are assumptions acquired before any critical empirical evaluation has taken place. To address this, the student must complete a prior audit. Before opening a single AI prompt, they must explicitly write down their assumption of how a truss distributes weight, and they must name exactly where they got that belief, whether from a textbook, a family member, or a feeling that it is simply obvious. Documenting these inherited priors early provides a baseline. Identifying these biases is the only structural mechanism that prevents a student from using AI to blindly reinforce an assumption they never actually tested. The student now enters Phase 1, Concept. Here, they use the large language model safely as a Socratic sparring partner, testing structural geometries to refine their theoretical mental model of the truss. The mandatory deliverable for this phase is a falsifiable hypothesis, written entirely in the student's own words without machine assistance. This hypothesis must explicitly predict a specific failure mode for their bridge design. If they cannot state exactly what physical conditions will cause their truss to fail, they have not completed the concept phase. They are merely preparing to build blindly. To verify that the hypothesis is the student's own work, educators often rely on AI detection software. This chart compares the false positive rates of AI detectors based on the author's primary language. It shows a low error rate for native English writing, but a heavily skewed false positive rate for non-native writing, rendering the software highly biased. Because these detectors are unreliable, we replace them with a structural requirement called a reasoning trace. The student must submit a prompt log showing exactly what they asked the AI, an annotated text diff explaining the major changes they made to the machine's suggestions, and they must be prepared to defend any claim in their hypothesis orally in class. Forcing this invisible reliance to become visible on paper protects the integrity of the assignment. It is the most equitable way to guarantee the student retains true epistemic ownership of the final idea. With the conceptual model finalized, the project moves into Phase 2, Constraint. This acts as the strict gateway between a pristine digital theory and unyielding physical reality. Before any construction is authorized, the design must pass through a 4-part gate matrix. The design is evaluated on safety to self, safety to others, the material ethics of sourcing and waste, and the scale of consequence, ensuring the student is not attempting to build an object that requires professional load-bearing certification. For the ninth graders' truss, these gates restrict the maximum weight load they are permitted to test, the type of joinery tools they can safely operate, and the environmental impact of the adhesives they select. These requirements map directly to what the philosopher Aristotle termed phronesis, or practical wisdom. He explicitly distinguished this ethical reasoning from mere technical skill, arguing that the ability to make a thing is incomplete without the judgment of how and why it should be made. If a design fails any of these 4 checks, construction is prohibited and the concept must be revised. By operating as mandatory physical requirements, ethical boundaries function as true engineering constraints, rather than superficial afterthoughts bolted on to a finished project. The project advances to Phase 3, construction. The student finally translates their digital, AI-vetted design into a tangible physical wooden truss, ready for load testing. This is the wall of reality. In a purely theoretical space, a student and an AI can generate an endless loop of justifications. For a design, a physical object terminates that open-ended debate. The object either holds the weight or it collapses. A successful structural hold is not the ultimate pedagogical goal. Under this framework, an AI-assisted project that functions perfectly is graded as incomplete if the student cannot explain its boundary conditions and identify precisely where it would eventually fail. When physical evidence shatters a student's prior assumption, it forces what psychologist Jean Piaget defined as accommodation, the active restructuring of a mental model to absorb contradictory facts. If the truss breaks prematurely, the student cannot simply shrug and admit they were wrong. They must refer back to their prior audit and explicitly articulate exactly what was physically flawed in their original mental model. The physical build creates a rigorous epistemological break, forcing AI-generated theory to survive contact with reality. To evaluate this process accurately, educators must implement a dual grading architecture that deliberately separates theoretical understanding from practical execution. The student's episteme, their propositional knowledge, is graded strictly on the falsifiability and clarity of their Phase 1 conceptual hypothesis. Their techne, or craft knowledge, is evaluated entirely independently, based on their physical execution and empirical testing during Phase 3. Within this dual architecture, a student might perfectly execute the concept but fail the physical construction. A failure in either domain is treated as a critical diagnostic insight into their learning process, rather than a mere point deduction. Applying the friction test to every task, demanding that students grapple with the core logic while using AI only to remove barriers to access, provides a blueprint for managing technology across multiple grade levels. This approach allows schools to scale complex inquiry-based curricula across entire districts. By using AI to adapt open educational resources into multiple languages and reading levels, educators can provide high-quality materials to every student without sacrificing cognitive rigor. A cognitive scaffold's ultimate job is to eventually come down. By forcing digital hypotheses to face unyielding physical reality, we ensure that what remains standing is a proven, reality-tested human mind.